Okay, so can I just ask people to bring some data up? I have two different situations. Okay, and we're going to share experiences.
好，接下来这个 section 呢，丽他想要分享，就是我们在各位做 N9 量测的经验。那台湾中心这边先提供2组 data 给丽，一组是在宜兰河的圆山大桥，那另外一组是在联保溪的五里林桥。那现在他秀的这一张是圆山大桥资料。那不晓得各位有没有带你们观测的资料？像云科大的学生，如果有的话，等一下你有给他吗 ？OK。如果有的话，他待会可以一起讲解。OK。
So the question before the break was, if you have a COV of less than 5 for your 5 measurements, is that an indicator that you have a good measurement? Okay? Because you would think if you've got 5 measurements and your COV is below 5, that you've possibly got 5 good measurements. So I was given 5 measurements here, and if I do Control and S, I get the summary of those 5 measurements, and we have a mean discharge of 3.9, and we have a COV of 2.6%. Wonderful. We've done a great job. Let's go home. Okay? No, definitely not. Definitely not. So if I take that away again. So if I just tab through these, can anybody just shout out things that they do not like about the data? What do you think? Doesn't matter whether it's right or wrong. What don't you like about the look of the data?
This is going back to what Lee was saying about when you QC the data. The first thing is qualitative. Just have a look at it. What do you feel? Do the first step in the QC is just to scroll through and look for anything strange.
As soon as I got these 5 data sets, I went, ugh! Okay, I didn't like the look of them. There's no science to that. It's just experience of using the instrument, and what it should produce, and what we've got here in front of us. You know what a river looks like, and how velocity distributions look. And you look at this and you say, this doesn't look naturally right. So, anybody, anything you don't like? Okay, I'll give some. So this, we'll just explain this first. Okay, so here we have some reasonable looking data, and this looks wrong. Looks wrong. It's actually possibly and probably not wrong. But what's happened is the instrument has switched from using high definition pulse coherent data here to using incoherent data here. Incoherent data is always going to be noisier. Okay? It's going to look more of a, in England we'd say harlequin data style. It's exactly as this looks, different colours. Okay? It's just noise in the data. Okay? It doesn't always mean that it's wrong, because often with the pulse incoherent, okay, the mean of the total depth is actually very good. Okay? It's just that cell by cell, it is noisier. Whereas with our pulse coherent, the high definition, it looks like that's what the water might be doing, sort of fast just below the surface and going down a bit, and slowing down, sort of getting towards the bed, which is the natural thing, the way we think about water distribution in the vertical. So that's first thing I don't like, but as I say, I'm not necessarily too worried about that. What I really don't like on this one is that we've got a straight line here, we'll follow that, and we've got pretty much a straight line here, and then as we go upstream at the edges. That doesn't surprise me. The water velocity's gone very slow, and okay. But here in the centre of the channel, we have an upstream movement. Okay, that doesn't look natural. Okay. Also, if you look at the vector of the velocity from behind, they're pretty much going straight down the channel, except for here, where we have this upstream bit, and all of a sudden our velocity is sort of very much skewed off to the side. That is definitely a moving bed. Okay? Everything about the way that the instrument is referencing the velocity is wrong. It's subtracting the wrong boat movement from the total movement to give us a velocity and direction. Okay? So, if I go on to another, you can just about see it there as well. We've got bad. You see at this break point here, we've got a step down, and then we've got velocity going off at an angle. That's a bad bottom track. Okay, or it's a bad truck reference, should I say. In this case, because I'm only showing bottom track, it's a bad bottom track reference. It's not impossible for a river to have velocities going off at angles like this. Very, if there's a lot of boulders in the river, that's quite possible. But any time where you sort of, normally you see in most situations the velocities going down the channel. If you start seeing velocities going off at an angle, start questioning your track. Okay, so I'm just going to try and look at it in a little bit more detail. So particularly on this one, because it shows up quite well. If I go to the time series, and one of the parameters I set up, okay, is the bottom track mean contrast. Okay? And it's where we're just looking at, from the beams, we're seeing the difference between sort of surface and the bed, the water and the bottom. Okay? And so the higher that value is, the stronger the interface is, or whatever. But we see here around about 3 to 5 meters.
Because the SNR plot, when it hits the bottom.
That's another way of looking at it, but it's not totally that. Okay. We can have a really good interface between the two, okay, and still have a moving bed. Okay, so it's not the only thing to be looking at. So here I'm looking at it's just how we're detecting the bottom. Okay, and you see how it's gone from sort of values that are up around about 20 decibels, 22 decibels, and it's gone down to 14. Okay, and it's jumping around, and that's between sort of distance of 2-3 meters to just short of 5 meters. And if we go back to the transect, where do we see that? Around about 3 meters to just short of 5 meters. Okay, so there's definitely a moving bed occurring in there. If we have a moving bed, our discharge value will be low. Okay, for sure. How low it is depends on the magnitude of the moving bed.
So, if you go back to the summer, discharge summer, so control gas summer.
Yes.
Right. So where's the COV? The COV is
2.6.
So the COV, you've done all these back and forth. This is the case I guess he's talking about. Back and forth. COV is very good, but it's not good data.
But it's not good data.
And that's the case because of bottom track, the moving bed.
Okay, I would have at this site, sorry, I'm now going to bring back in GPS data. GGA, which is the corrected data, which is the one that gets corrected from the stationary satellite, and the VTG, velocity track over ground. Okay.
We can plot just GGA and VTG and see the difference, and then maybe it can multiply.
Okay, so the GGA, if we look at that, that's the dark colour one. It's should be purple. I don't know how it's showing up. Yeah, it's showing up purple there, but it's definitely no good. We've definitely got a multi-path error there. When we get this big jump in position from the GGA data stream, that's a multi-path error. Okay, so I can't use the GGA, so I'm gonna ignore that one. I'm gonna go to tracks, and I'm just gonna disable that from auto-stream. So I would hope that what I see, that's blowing me out the water. If I just scroll through Control Tab, if I Control Tab for all of them, I don't. Okay. Right, so first things, you would hope that they would overlay each other perfectly. That would be the ideal situation. Why is this one not overlaying? Okay. So I'm going to turn on the toolbox, Control T, and I'm just going to have a look at some what I've got set up in here. Sorry. I go to first of all, have I got a magnetic declination set in there? No, I don't. Okay. So for the GPS data to be valid, we need to have a magnetic declination set in there. So if it's 0, that's no good.
It's minus,
there are very
minus 3 is here.
Minus 3 here. So can I assume that that's about right? For
That's around -3.
around -3. So I'm going to put in -3. And I'm going to apply that to all. If I click apply to all, it applies it to all 5 files that have been opened. Okay, see, so brought it back a little bit closer.
Yes.
Okay, but it's still not there.
Yeah.
Okay. So I look here at this value, GC, BC. It's the GPS course to the bottom track course. Okay, and it's saying that there's a 7.7 degree difference between those two. You then sort of say, why have we got that? Okay. Bad compass calibration. That's normally the case. Okay, bad compass calibration. Let's have a look at the compass calibration. So if we go Smart Page, we have this same thing. No compass calibration. So let's make it easier for you to see. Okay. So I don't know whether everybody here is not doing compass calibrations, or there's something strange that's occurring that we're not recording the compass calibrations. But that's now 2 different sites. We've got exactly the same. And this, when we get this date, that is the default date that the instrument comes out with from San Diego. Okay. So that is the last time that so what San Diego would have done is they would have put the compass in the instrument and they would have calibrated it and they would have done something else and they would have done other work and everything. And then before it was, after they'd done all their tests on it, they would have they would have gone back to system defaults. Press that so that your instrument is clean of all their tests. And when it goes back to system defaults, it resets the date, the 1st of January 2000 at midnight. My feeling is, I'm not saying it is, it could be an error that's happening on the instrument. My feeling is that this instrument actually hasn't had a compass calibration. And it's using its default calibration that's in there, that is actually a meaningless calibration. Okay? And that's why, when we go to the transect, we're seeing this variation. Now I can apply a correction for that, but it's only a correction that goes linear, whereas a compass calibration isn't necessarily linear. Okay? So we really should do a compass calibration because that will apply offsets in the calibration for the different magnetic interferences as we're going around. Okay? If I want to apply a linear correction, if I bring the toolbox back, I can say I know that my GPS course to my bottom track course is 7.7 degrees. In SonTek compass heading correction, if I put in 7.7 and only apply this to an individual file because it will change from file to file, I'll put that in there. If I apply it, okay, it's not overlaid it, but it's very, sorry, to my eye, it's very similar. But what we're seeing with the bottom track is, the bottom track has gone upstream of the VTG track. Okay, so they've started in a similar place, it sort of ended in a similar-ish place, just short of. That's sort of another indicator of a moving bed.
So when you do the calibration, the output and the discharge should be changed.
Yes. So I don't think, if you're not going to do compass calibrations, as I said earlier, please, please, please do a single calibration in a really good site, okay, and leave that one applied onto it. This one is applying a meaningless calibration to it. That is affecting the data. What else did I look at? Now, could I actually trust the GPS data? You know, I know we had multi-path error, or maybe it just. So I'm looking here at the number of satellites we're seeing. That's what's plotted in red, and in blue, a value called H-stop, the horizontal dilution of precision. Okay. If we have an H-stop that is greater, and I personally say greater than 2, but some people sort of go as far as 5, but I often see poor data at 5. An H-stop greater than 2, I don't use that GPS data. Okay, and this has gone up to an H-stop of 8.
Yeah.
Okay, so that's, again, that's where the H-stop is where the spread of the satellites. So we could have just 4 satellites, and we can have one over there, one there, one there, one there, and we get a really good H-stop, because the angles and everything to the antenna are great. We could have 8, they're all directly above us. I know it never happens, but let's just say it could. You could have 8 there, but because there's not a good spread, we'd have a really poor H-stop. Okay, and it's to do with the precision that it can actually calculate its position. Okay. For the GPS to work, for differential, it has to have 4 satellites. For RTK, it has to start with 5 satellites. And obviously, the more satellites we have, the better we get. Okay? I typically like to see a minimum, at a push, 6. Normally 7 is what I like to see. 7, 8, 9, 10. So.
Because you may start with 7.
You may start,
and
yeah.
then it goes down.
It does. It's also better if you have, let's say you have 6, and you retain 6 the whole way, and there's not a change in the number of satellites. And a key thing to that is that you keep at least 4 satellites common to the whole measurement. So throughout that measurement, you stay with at least 4 of them for the whole measurement. Okay, it's no good having 7 satellites, but sometimes it's that one, other ones come into view or whatever. Okay. So with this, we've had satellites starting at 6, and we ended up with zero satellites. The h-stop stayed relatively high because what happens is, if it has received a correction, it retains that correction for up to 45 minutes. And there's a value called GPS age that tells you how long that's been.
I have a question.
Yeah.
But we got enough satellite, so we can use the GPO or VTG more. And sometimes we also cannot use the park and track to determine the, because the moving bed. Yeah. So what else can we do?
Well, from the satellites, well, if you don't have enough satellites, you can't use VTG or VTG works better than GGA with less satellites. Okay, it's just a track across the ground. VTG is no good if the boat is not moving. If the boat stays stationary for any time, the accuracy of VTG goes. It has to be travelling at about 10 centimetres a second or more, okay, for that to be valid. Okay. You will not get multipath errors with VTG. Okay. As, sorry, it's no use for you at the moment, but as better systems, GPS systems, become available, we will feed them into the instrument. You know, there's now some of the manufacturers, and the manufacturer that we use at Hemisphere now have just released a GPS board that has GPS. So sorry, we should never call it GPS. We should call it GNSS, because GPS is just the American system. China have, I don't know how you say it, they do? They go, okay. And they have Dago 2, just coming online. In Japan you have QZSS, is it?
That's the polar one, yeah.
And then, the Russians have GLONASS, okay. This new board from them has the capability of using all of those. So that means we're getting more and more satellites, with more and more sort of stationary satellites available and land-based correction things being available. You know, and it means and dual frequency rather than single frequency. Okay, so it actually means that we're getting more and more precision from more and more satellites. Or even if we have less satellites, we can have more precision because of the dual frequency.
And I think in our new release, customers will have to pick.
They will be able to do that.
Oh, you can pick, I want Dago, or I want GLONASS.
Hemisphere only sent that to us for trial a couple of months ago. And so it's in the pipeline. It's in the pipeline. It will happen. And I'm sorry for those who already got it. You know, it doesn't help you. But you know, we are sort of aware of the problems that you have, and we're trying to sort of sort that out. New antennas, even. You know, changing antennas. You know, Hemisphere just released a new 845 antenna. You know, that's far less susceptible to multipath. It works better under trees. Okay. So things like that. You know, that's technology moves on. We all know that. You know, and we're trying to encompass that as quickly as we can. So what else? We obviously lost some bottom vertical beam here. The vertical beam on the M9 only works from 40 centimetres, or 40 centimetres below the transducer.
So for shallow flow.
So this vertical beam, because it's 500 kilohertz, it has to have a larger blanking distance. Okay, so we need to have we have a blank here of 40 centimetres before it starts working. And if you look at this, we lost it at around about 60. I don't know what in front of we have the transducer depth of 10. So we've got 10 centimeters, okay, below there, below the water surface, plus that makes 50 centimeters. Okay, blanking on all that. You know, so it's quite likely that that's not going to work. So what it does in those situations is it switches to using the bottom track for depth. Okay, those will work down to 15 centimeters. Control T to take that off. We see here I have boat speed plotted and boat speed to water speed. So you see that the boat speed was actually quite variable. Again, it would be better if the boat was going at a nice steady speed all the way across the channel. You know, it went from 0 at the edge, well you'd expect that, up to about 0.8 meters per second across the channel. And then it went down to 0. And then it went up. Now maybe that's because it's a bad bottom track. Maybe it's because it's got stuck in the eddy of a bridge or something like that. I would suspect it's got stuck because it then went from 0 to 1.4 meters per second. So I imagine it's got stuck in the eddy, and to help get it out, somebody's gone and pulled the boat quickly out. Okay, so just try to sort of get the smooth movement of the boat. You know, that will help a lot. If we go, the instrument, and we were saying earlier about it was switching between pulse coherent and incoherent. Okay, it depends on the water depth, the water speed, and the boat speed as to which one it actually chooses. Ideally, we want it to be using pulse coherent all the way across the channel. So to keep it in pulse coherent, we really want this boat to be moving nice and smoothly. Okay? The moment there's a rapid movement or anything, it plays safe, the instrument, and the safe one is incoherent. Okay, because there's no ambiguity errors with incoherent. There's no, yeah, and we're just using the Doppler from the single pulse of sound. It's very robust, not very high resolution, but very robust. So where it's switched there, well, very quickly, it's switched back into incoherent mode. Okay. For discharge, that's okay. We'll still get a reasonable discharge if everything else is okay, bottom track and everything. But we lose the visual effect and the high resolution of pulse coherence. Okay. Yeah, I've got a little bit more. Sure,
Go for it. Then we'll fix this.
Where's that one first?
Oh, you want
The station.
Yeah.
So at this site, I couldn't trust the GPS. I couldn't trust the bottom track. So what would I have done? I would stationary, okay? Undertaking a stationary measurement, okay? Where we sort of put the instrument at a point and we say, this is where you are, okay? And we just allow it to collect data for 30, 40, 50, 60 seconds, whatever is your standard here, okay? And just, it doesn't have to worry about where it is, you tell it where it is, and it just collects velocity data. It's okay if it moves around like this, as long as it's random. If it's sort of always heading off over to the left of the channel, or always heading off to the right, or you're allowing it to drift downstream, that's not good. If the movement is random around the point, that's fine. The math will cancel each other out, all that error. So that would be the thing to be using there. Okay. So then somebody gave me a data file they had from stationary, but was not so good. Okay. Okay, so this was the site.
This was the site.
Do you want to show the video? Is there a video?
I think it's just a photograph.
There was a video.
Oh, there is a video.
Oh, here it is.
先说明一下？没关系啊，不然我们不知道什么情况，你说明一下。
It looks like a typical wet day in England to me.
就是我们在台风天的时候，在访寮那边有一个试文机，试文水库雨林地的下游，然后在那边做全工程观测。
全工程。
对，然后就是这里的那个浓度大约是3万到5万ppm，所以这是我们的跑出来的图，就是那个 button check 跟那个
GPS
的那个画出来那个图就很广，而且就是我们的水深两侧也是很好，对，就是会出现一些问题。
Yeah, just helping understand that. Okay, so it's pretty fast. Not silly fast, but it's quite fast. The boat's bouncing. That's always a good indication that it's quite fast. So when the boat's bouncing, the instrument's also bouncing out of the water. That's never good. We never want to have the transducers come completely out of the water. Also, just looking at the way it was operating and the way it was bouncing, I would imagine, and tell me if I'm wrong, but I would imagine that the transducers were pretty flush to the bottom. Is that right?
是跟它切起放吗？
没有，再深一点点，大约3到5公分。
凸出来有凸出来。
对对对。
How much out is it?
Maybe 3 to 5.
About that much out.
Okay, so a little bit of that. In really fast flowing water, okay, I really recommend that you protrude the instrument out quite a bit more. Okay? I know we lose some of we're losing even more at the top. We're going to have to extrapolate more data at the top. But what happens if we don't do that is the water is really creating a lot of noise around the transducer. It can be physical noise, banging on. It can be aeration, being little pockets of air, little bubbles forming around the transducers. So if we put it deeper down in the water, the surface hits here, all of that noise, all of that aeration passes around the side and rather than going under. Okay, so we're able to have our SNR value. So an SNR value is a really key thing for the instrument. The SNR is signal to noise ratio. So the amount of signal that is coming back from the water in relationship to any noise, either electronic instrument noise, or some noise that's being generated around. So that's this top left plot, the SNR. So we would maintain a better SNR. With a better SNR, we can profile deeper. Okay, so
we think this is about 2 meters?
Yeah, in this case we were losing. The instrument wasn't even being able to detect the bottom and that's with 500 kilohertz. My feeling, if we look at the top left plot, this is the 4 3 megahertz beams that are being plotted here. When they are detached from each other like that, there is definitely aeration occurring. Okay, either pockets of air or bubbles of air all around there being formed. That's never a good sign. It's not good for the data quality, and it's definitely not good on the range that we can get. Okay. If we're to just put it deeper in the channel, we would have solved a lot of those problems.
first thing is to push down.
We'll do that.
We can do that later.
Even though it's not detected the bottom, well, because it's not detected the bottom, we've actually got some unusable data. Okay? The instrument, you know, in that channel there with that really sort of almost like running mud going down the channel, it's not always going to detect the bottom, unfortunately. Maybe you have an external way of detecting where the bottom is. It could be GPR, the ground penetrating radar. Maybe it's a simpler thing as a big weight that you actually drop down to the bottom of the channel and you just plumb the depth of the channel, okay, to measure that. If you can do that, then if we double left click here, and if we put in a value where it says user input of water depth, if I put 3 in there, okay, it will say that that is the depth of the channel. Any velocity information that it's got, it will then extrapolate that down to the bottom. It will give us a better chance of having a usable data set. It's not helped in this one because here our SNR has already gone to 0 at 60 centimetres. Okay, so that's probably the error that's reduced our range on that one. You can only do this in stationary. Okay, it would be really nice, and it's something we keep pushing the software people to be able to do that in RiverSurveyor, to manually or transfer a file in, telling the instrument what shape what depth the channel actually is. We'll keep pushing. In other sites, this one. Okay, so you see this column here. I'm just going to program in put in a depth of 2.5 metres. And we've now got velocity information to deeper down. It's not good velocity data because of the noise being generated. But if we'd have had this instrument deeper in the water, and we were not getting the background noise that was being generated, we'd have had much nicer data. The top data is quite good. It's only that over range, because of the noise, it's getting poor data there. So I think we would have got a very usable profile there simply by lowering the transducer down into the water. You look at the SNR plot, it's not perfect. But we have the green, the blue and the yellow, beams 2, 3 and 4 overlaying each other. Beam 1 is very slightly offset. Okay. In stationary mode, we tell you to orient the instrument like this, with the cable coming out the back. So it's coming out the back here. You'll also notice that if you follow that down, that there's an arrow here pointing to this transducer. That is beam 1. Okay? What we get is the water coming here, and as it goes over this peak here, it creates an air pocket there. That's why we have that separation there. If we'd have just lowered it down into the water a little bit more, okay, we would have lost that. That would have come back. But all 4 beams were looking like they were one. Any questions? Or any more data? Or any more data? Yes. tomorrow we will definitely we'll try and do a good setup out in the field, and we'll do a not so good setup. Sorry, how many instruments have we got tomorrow? Do we have one or two? One. Yeah, we'll probably go across with a good setup, and then we'll do another one that's not so well set up, and see if we get a different result.
We will try moving forward.
We'll try moving boats, we will do the loops, we'll do
Probably
moving bed tests.
do the loop method.
Okay.
Can you show me how to interpret the function in the RS and RiverSurveyor line, especially the function in the button track?
Okay. Sorry. So you want to see how? Sorry. So you want to show how to activate this? Is that what you mean? You want to know the meaning of?
You want to understand each one of those?
Yes.